So we're going to add some vectors and then we're going to jump into a couple other topics as we move through. Okay, that should be easy enough to see. That should be better enough for you guys to see. So what we're going to do is we're going to add these two vectors, but we're going to use the parallelogram because these aren't a Cartesian vector system. So this one isn't Cartesian, and so we're going to do those. So what you want to do, okay, is as we draw our vectors, I have this vector, which is on the V axis. And if I have this line out this way, this is 30 degrees. And this is going to be my F1V vector. And then my F1U vector. And that one is going to be 45 degrees. And this is my F1 vector. This is what we've got it on its components, and this is my 4 kilonewtons. So what we did is we took this one and we did its projection onto the U axis and then onto the V axis, and then did its projection onto the U axis. And so now you get this vector here that you have that part. So you can break this vector up into its V components and its U components by using your good old signs, okay? Because we know that this is going to be 105 degrees, because we know that the angles inside of the triangle end up being 180 degrees. So if I'm looking for this side, F1V, that's going to be my 4 divided by the sine of 105 is going to equal my F1V divided by the sine of 45. So you can get these weird components on not a Cartesian coordinate system by using the law signs. And I think you got a couple of homework problems that kind of refer to that. So just wanted to show that part before we dive into looking at a few other fun things. Okay. So we've talked and we've played with components. But one of the components I want to play with a little bit differently is to remind people about other coordinate systems. It's been that kind of a morning, folks. Okay. So we started out with our basic Cartesian coordinates. And if I'm doing this, this is going to be my X, this is my Y, and this is my Z. Just as a reminder, I hat is a unit vector in the X direction. J hat is a unit vector in the Y direction. And K hat is a unit vector in the Z direction. But we can do our components a little differently. So if I have another vector, so I'm going to take a vector out here. So this is my vector R. And I come in here and I'm going to do my 3 components. And this is where you learn to draw in 3 dimensions pretty well. we have our X, Y, and Z components. Now this, I can also have this vector. This is the projection of this vector onto the XY plane. So we talk about vector projections because we can have this is in the XY plane for that vector. And now we can look at different angles. And you're going to see different angles for this vector. You'll have a vector, an angle that comes from the Z to the R. Hang on just a second. Yes, sir. Yeah. Okay. Okay. Yep. Understood. Understood. Hey, I'm in a class, so I'll call you back later. All right. Bye. Yeah, it's been weird. Okay. So you get this angle here, and you'll see these as alpha, beta, and gamma angles. Or you'll see them as theta X, theta Y, theta Z. But you're looking at the angles from the individual axes to that vector. So you'll get those individual axes that you get. And so if I'm looking at R in the X direction is going to end up being your R cosine. And if we do this as theta, we'll do this as theta Z, and we'll do this as theta Y, and we'll do this as theta X, but you can have them as alpha, beta, and gamma. But you'll get your X projection as that. You'll get your R cosine of the vector in the Y direction, and you'll get your R cosine in the Z direction. And just as a reminder, cosine squared X plus cosine squared Y plus cosine squared Z is going to equal 1. Because you're going to see those in other items. And then we can do your I, J, and K's, just like what we've been doing before, but you're going to have those different component pieces. But don't forget that my cosine of X is going to be Rx over R. Cosine of theta Y is going to be Ry over R. And cosine of theta Z is going to be Rz over R. And our book does alpha, beta, and gamma. So, but you'll see both notations around, and you'll be able to work in those notations because we will be working in 3 dimensions. Life is always more fun in 3 dimensions. So we have those pieces that we've got. So just another reminder is if I start with our components, right? So we've done our various pieces. So we'll do our Cartesian coordinate systems. Think of 9th grade geometry, right? So here's my X, my Y, and my Z. It helps me to put in items so I can kind of keep track. And this is where engineering paper comes in really handy, or the isometric paper comes in really handy. But let's say we are going to put an anchor at this position here. And that anchor is going to be such that this is 3 and this is 2. And it's in that XZ plane that I have. Now I'm going to put another anchor up here, except this anchor is going to be kind of in space. This is going to be 3. This will be 4, and we'll make this one 1. And what we're ultimately want to do is we want to find that vector. All right. We want to find that vector. We want to take the difference between the 2 points. So remember that way back when we did the distance between 2 points. So this point here, just so that we have it, okay, I'm in the negative 3x. I'm in the positive 4y. And I'm in the 1z. This point is in the positive 3x, the 0y, and the 2. So if I know those 2 points, and I can look at those 2 points, I can look at if I wanted to make this vector so that's going to be vector RA, right? And then I've got this vector. This is vector RB. RA, actually, we're going to do it this way. We're going to do RB plus R is going to equal RA, because that's my vector addition. I'm doing head to tails, so I have all my directions correct, because that's one thing as you guys get into what we're about to do is trying to keep your directions correct. And a lot of times you'll end up backwards, upside down, and all over the place. So you want to make sure that you've got your vectors there. So this, we're doing head to tail. So I did my RB plus my R will give me RA. So R is going to equal RA minus RB. Now we can go through and do the mathematics, right? We can look at R now becomes R XA minus XB in the I direction plus X or YA minus YB in the J direction plus ZA minus ZB in the K direction. And it's something we've seen before, right? We've seen this before. We've done these before. So we can actually do that calculation, right? So my R is going to be 3 minus my minus 3 my 0 minus 4 and my 2 minus 1. So I'm going to get 6i minus 4j minus plus 1k. Just something to remember. The other thing that we have to do is my vectors. So if I have a force vector, I can do my force vector as a scalar times a unit vector in the unit direction. So I can get my force vector, my unit vector. So my unit vector is going to be whatever my r is, my vector r, divided by the magnitude of that r. Okay. So I'm going to do a drawing here. So this is going to be 18 feet, and this is going to be 12 feet. And my vector is 36 feet. So we have a cable under tension, and it's going to be 700 pounds. We want to find our unit vector. Well, that's easy enough, right? My RAB is 18 in the I direction minus 12 in the J direction. We're going downward in the Z direction, so this is a minus 36 in the K direction. The magnitude of RAB is going to be 18 squared plus 12 squared plus 36 squared square root. And when I do that, that's 42. So my UAB, my unit vector in the AB direction, is going to be 18 divided by 42 in the I direction, minus 12 divided by 42 in the J direction, minus 36 divided by 42 in the K direction. And if I do that, $18 divided by 42 is 0.428. .286. .857. And if I want my force vector now for that 700 pounds, I'm going to take my 700 pounds, multiply it times my unit vector, And that equals 300 I minus 200 J minus 600 K. Now, talked about projections. Okay. So now I want to find the projection of my force vector on the z-axis. This will give me my force vector dot product with K. This is where we're going to get our dot products are going to come in. Move that down so everybody can see that a little better. Remember that, move this all back down. I dot K is going to equal 0. J dot K equals 0. And K dot K equals 0. So if I'm going to do my dot product for my projection, this is going to be my 300 I minus 200 J minus 600 K dotted with my K axis. And this is going to end up being minus 600. If I'm looking for the projection on the z-axis. This would also be the magnitude of the force acting in the z-axis. Are you kidding me? Apparently, I didn't bring all of my notes downstairs. Not a surprise for today. Not a surprise for today at all. All right. That just tells me that that's the way it is today. Yeah. All right, so I'm gonna stop recording. But Friday,